Good morning, everyone. My name is Ivan Strasnicki. I'm a technical fellow with Curtiss-Wright. For the next 20 minutes or so, we're going to learn about high-speed signal integrity in the context of VPX modules, backplanes, and systems. And I say we because I'm relatively new to this area. However, one thing I do know is that if there's any area of electronic design that deserves the label of hoodoo voodoo, it's SI. I think everyone would agree with that. So let's start with some basics, beginning with the serial signal transmitter and receiver and the channel upon which the signal travels. I'm showing here a physical schematic out of the VITA 68 channel compliance standard. And it shows the various parts and interfaces that are involved in transmitting a signal and that you have to be concerned with to figure out what specific maximum speed you might be able to transmit over that channel. A couple of measures of goodness of these channels. One is bit error rate, which is typically needs to be at 10 to the minus 12 or better. The other one is an eye diagram, where you need to have some kind of an eye opening for the data transmission to be seen, so to speak. So both of these are measures of goodness that tell you whether or not you're being successful with your channel design and with your data transmission ultimately. So that all seems pretty straightforward, right? Where's the hoodoo voodoo? Each of the parts and interfaces along that channel that I just showed has its own unique electrical characteristics. And the devil's definitely in the details here. Those parts and interfaces have so-called S parameters, things like insertion losses, return losses, crosstalk, caused by effects like impedance mismatches, parasitic inductance and capacitance, and weave skew. You can see I've learned all the buzzwords so far. And each one of these parts and interfaces needs to be considered to ultimately figure out if you can transmit successfully along that channel. Another way of picturing this is something a little simpler. If you can picture your favorite sports car on one of these two roads, one of which is straight and smooth, the other one not so much. It's pretty obvious which one you'd choose if you wanted to bury the speedometer needle. I was meant to mention a 10 gigabit per second speed bump. I'll mention it now. It's actually more accurately 10 gigabaud. The reason I mention it is because back when VPX was originally developed, and I think one of the previous presenters yesterday might have talked about this, maybe a couple of them. The VPX itself, in particular the connector system, was known to be rated at 6.25 gigabaud. So the Gen 1 fabrics and protocols at the time, things like Serial Rapid I/O Gen 1, PCI Express 1.0, which were at 2.5 to 3.125 gigabaud, were relatively easily implemented with the rating at 6.25 gigabaud. Moving on to Gen 2, with fabrics like Serial Rapid I/O Gen 2 and PCI Express 2.0, which run at 5 to 6.25 gigabaud. It can still be implemented, but now we're at the advertised limit of the connector, so we need to start paying a little more attention. Fast forward to Gen 3 with fabrics like 40 gig, 10 gig KR, and PCI Express 3.0, and the hoodoo and gree-gree need to come out. That's really the point at which we need to start paying a lot more attention to design rules. In particular, at the time, this was probably about 2 or 3 years ago when Gen 3 first started to be implemented, it was discovered that there were a couple of parameters of the VPX channel, in particular the connector system, that were critical. One was the return loss. The other one was a parameter known as the insertion loss to crosstalk ratio. And those were both very fundamental in understanding and mitigating to be able to implement Gen 3, and both had to do with the footprint of the connector on both sides, both the module and the backplane side. With the right voodoo kings and queens at your side, though, Gen 3 can be implemented, and our efforts in this area around 2 or 3 years ago resulted in our Fabric 40 solution, which is part of now the wider Gen 3 ecosystem. I want to spend a couple of minutes on Gen 3 in a little more detail because it's instructive to any future generations, things like Gen 4, Gen 5, et cetera. Our Fabric 40 solution consisted of a wide range of activities and a lot of work. Started off with a large signal integrity simulation project. Moved on, that led to crafting of new design rules, which then progressed into product design, development and substantial testing, and ultimately proven products and deployment into the Gen 3 ecosystem, which is, like I mentioned earlier, has been around for a couple of years now. The signal integrity simulation project in particular was key to all of this. It really allowed us to look at a variety of scenarios, and you really have to look at more than even just 2 or 3 scenarios. It also allowed us to identify specific areas or hurdles like the return loss and the ICR parameter that I mentioned earlier. And then last but not least, it allowed us to put into place mitigations and test different features that will work, and some of which will work better than others, and some combinations of which will work better than others as well. So all that, and at the end of all that, a lot of testing that had to, there's one thing to do simulation, of course, you do have to end up testing in the physical world and make sure that all of this works. And long story short, we were able to deploy Gen 3, and other people have been able to deploy Gen 3 as well successfully. And the key bottom line statement here is that it was discovered even in the SI simulation project, as well as all the testing, that we had a significant margin. You can see a couple of the eye diagrams with quite low drive signal amounts, leading to pretty good eye openings. Now we get to the present. Gen 4, PCI Express 4.0, impending ratification of that standard. It should be this year. And that will result in signal speeds of 16 gigabaud, 60% increase over Gen 3. This is considered, or it can, actually some presenters have already mentioned that this is a possible breakpoint of VPX at which we need to start thinking of potentially newer proprietary connectors or even go optical. Well, I'd like to announce that our new Fabric 64 capability allows us to meet that with the standard VPX connector. So we don't see that to be the case, that the VPX is not going to be broken with Gen 4. We've proven to ourselves and are showing customers that with this new capability, we can implement Gen 4 using the standard VPX connector on OpenVPX with the right design rules. So what do I mean by that with the right design rules? These new optimized designs, and I've thrown in a smattering of some of the results, but the bottom line is that these new Gen 4 designs, we've proven, have resulted in 7 orders of magnitude improvement over Gen 3 in the bit error rate. Now that's really significant. You can see, for example, the insertion loss improvement, the return loss improvement, and then the original pass or go-no-go gauge that we used for this was something called COM, or channel operating margin, but since then we've migrated to the PCI SIG CSIM tool. Now at this point, you can see that we've been able to do a lot of simulation here. We still need to do some testing. But at this point, we're confidently stating that Gen 4 VPX can be implemented in OpenVPX with margin with the right design rules. That's not the end of the story, because Fabric 100 or Gen 5 protocols like we saw that earlier, 100 gig KR Ethernet, some of the proprietary protocols like Intel OmniPath, all of those are running at about 20 to 25 gigabaud lane speeds. And if we really want to extend VPX, we're going to need to be able to implement those protocols eventually. We've done some initial work there, nowhere near being finished or even at a midpoint for that matter. But we're, let's say, cautiously optimistic that Fabric 100 is going to be able to be implemented within OpenVPX and VPX. And that will allow us to continue to push out the VPX and OpenVPX capabilities for critical defense and aerospace systems.